In the previous lecture, we have started to deal with a very important chapter in solid state physics, and that chapter was actually free electron theory of metals. And in that first lecture on the free electron theory of metals, you have seen a brief introduction regarding this free electron theory. Now today it is our second lecture on this free electron theory of metals, and in this lecture we are going to see uh, a part of the Drude-Lorentz classical theory, which is also called free electron gas model. In fact, this Drude-Lorentz theory is a classical theory because you will see that in this theory electron, which is actually a quantum particle, that has been treated like a classical particle obeying the classical laws of physics, that is Newton's laws of motion and the Maxwellian distribution of velocity. Okay, so this Drude-Lorentz theory is the basic theory, and this, or you can say that this is the first theory on free electron theory of metals. Actually, in 1900, Drude proposed that the valence electrons of the atoms of a metal just behave like the molecules or atoms of a gas, and that's why this theory is also called free electron gas model. Okay, so first of all we will see what are the basic assumptions made by Drude in developing his theory. Actually, after the Drude approach, Lorentz treated the electrons as the particle obeying the Maxwell-Boltzmann statistics, and so this theory is also called Drude-Lorentz theory. Okay, so but what are the important postulates or basic postulates on which this theory has been built up? First of all, we will see. In fact, the theory in this theory it assumed that the metal consists of lattice of fixed positively charged ions in which billions and billions of valence electrons are moving randomly at a speed which at room temperature, that is you can say 300 Kelvin, in accordance with kinetic theory of gases, is given by this formula. Vrms, you know, is equal to 3 kb T over m square root. Here you know this kb is the Boltzmann constant and m is mass of the electron. Okay, actually this formula you know is for the speed of perfect gas or ideal gas, speed of molecule of perfect gas. But the same formula according to Drude model can be applied to find the RMS speed of the randomly moving electron inside the metal surface. Okay, so what this postulate says, in accordance with this postulate, if you consider that this is a metallic specimen, then in this metallic specimen there is a lattice of positively charged ions. It means in each atom the valence electrons are detached from the atoms and they move freely inside the metal surface, but the ions which are very heavy, they remain static. So in this positively charged background the valence electrons moves randomly just like the molecules of a gas. Okay, and so its speed can be found by the classical kinetic theory, and so that is given by Vrms equal to a square root of 3 kb T over m. And when you will substitute the numerical values, you know kb is 1.38 times 10 to the power minus 23 and mass of electron is 9.1 into 10 to the power minus 31 kg. And considering the room temperature at 300 Kelvin, it is found that this Vrms is almost equal to of the order of 10 to the power 5 meter per second or 10 to the power 6 meter per second. So the electrons, particularly the valence electrons, move at a very high speed inside the metallic surface. Okay, this is the first assumption. Okay, as I have told you that according to Drude model, the behavior of these free electrons are just similar to the atoms or molecules of a perfect gas, and so these free electrons are also called free electron gas. Okay, and accordingly this theory is called, also called, free electron gas model. Okay, in fact, according to Drude model, these free electrons are responsible for conduction of electricity in the metal. Metals are conductor. It can conduct electricity. It can also conduct heat energy. But which is responsible for this conduction? How this electricity is conducted? Actually, this theory says that the free electrons are responsible for electric conduction. Okay, and that's why these free electrons are also called conduction electrons. Okay, these are called conduction electrons. Now, the another postulate of this model says that the conduction electrons move in uniform electrostatic field of ion cores, and therefore its potential energy remains constant. Okay, and for simplicity in general we take its potential energy equal to 0. That is, you can say the interaction between the electrons and the ion cores is completely neglected in this theory. It means in this theory it is said that there is no interaction between the electron and the ion. Although ions are positively charged, electrons are negatively charged, and in the background of ions electrons are moving, but the interaction between the ion and the electron has been neglected in this theory. Although this is a drawback, you will see later on. But in developing his theory, Drude assumed that electron and ion do not interact with one another, and so it is assumed that the that the electron has zero potential energy, because you know potential energy is energy of interaction, and since there is no interaction between the electron and ion, and also it is assumed that there is no interaction between the electron and electron. So in the Drude model it is assumed that there is no electron-electron interaction and no electron-ion interaction. Since interaction between ions and electron are neglected, so the interaction energy will be 0. That's why in Drude model it is assumed that the free electrons move in the background of positively charged ions, but these electrons have no potential energy. Its potential energy is 0. And if its potential energy is 0, you can say that according to this model, the total energy of free electron is in the form of kinetic energy. So these free electrons has only translational kinetic energy, just like the molecules of a perfect gas. You know, in case of molecules of a perfect gas, we also assume that there is no molecular interaction, and so that the total energy of molecules of a perfect gas is has only kinetic energy, only translational kinetic energy. Just like that, according to Drude model, the free electrons has only translational kinetic energy, and so you can say that the total energy is equal to its kinetic energy. Okay. But one thing here has been also assumed, that if you consider that this is a metallic specimen, then the electrons move randomly inside this metallic surface, but no electron escapes through the surface. It means electrons do not leave out the surface. But how? Actually, for explaining this, why electrons do not escape through the surface of the metal, in this Drude model it is assumed that the energy of the electron just inside the metal surface is less than the energy of a stationary electron just outside of the surface. If you consider that there is an electron, let us say this, which is interior electron just inside the surface, and this is an electron which is just outside of the surface, out, and this is in. In this theory, it is assumed that the energy of an electron just inside the metallic surface is less than that of the energy of electron just outside of the surface, and this energy difference is equal to V naught. So you can say that actually this V naught acts like a potential barrier, and due to this potential barrier an electron cannot escape through the surface. So I have written it here. You can see the movement of conduction electrons is restricted within the crystal. So potential energy of a stationary electron inside a metal is less than the potential energy of an identical electron just outside of it. This energy difference, which is denoted by the symbol V naught, serves as a potential barrier, and this stops the conduction electron from leaving the surface. Okay. Actually, in this figure I have shown a one-dimensional potential barrier. Okay, one-dimensional potential barrier, and so you can say that the free electron move in a potential box. Okay, potential box. This can leave through the surface only when the potential energy of this electron will be made just equal to V naught or greater than V naught. Only then it can escape through the surface. Okay, but in normal condition the free electrons move inside the metallic surface, but they do not escape through the surface. Okay. Now, as I have told you that Lorentz modified this theory by considering that the electron gas obeys Maxwell-Boltzmann statistics. So this is a classical theory, you can say, because Maxwell-Boltzmann statistics, you know, is a classical statistics. The particles obeying this statistics is called a particle, is a classical particle. So in Drude-Lorentz theory, electron has been treated like a classical particle. Okay. So these were actually the important assumptions of Drude-Lorentz theory. Okay. In fact, this theory has been has successfully explained so many properties of metals. Okay, because you know the validity of any theory depends on the fact that is the theory explaining the important experimental result or regarding the system or not. So if this Drude theory is correct, then definitely this should explain the properties of metals. So Drude model has been used to explain some of the important properties of metals, and what are those properties? I have mentioned it here. You will see that this theory explains the validity of Ohm's law. It means you can see when we will apply this theory, we can easily see that metals obey Ohm's law. Okay. The electrical conductivity of metal has been also explained on the basis of Drude model. Okay. The thermal conductivity of metal can also be explained by the concept of Drude model. Okay. Again, we will see there is a famous law relating the electrical and thermal conductivity of metals, which is called Widman-French law, and that Widman-French law can be derived, can be explained on the basis of this Drude model. Okay. Again, the metal has a high luster and complete opacity, and this high luster and complete opacity of metal can also be successfully explained by Drude model. But in this lecture, I am just going to see the explanation of the first two applications, the validity of Ohm's law and electrical conductivity. We will see in this part of the lecture. But in our forthcoming lecture, we will see how this theory can be used to explain the thermal conductivity, the validity of Widman-French law, and the high luster and complete opacity of metals. Okay, so let us see how this Ohm's law, which is a very famous law for conductors, can be explained on the basis of this Drude model. Okay, let us see. So I have mentioned it here as a heading, that electrical conductivity and validity of Ohm's law. Actually, according to Drude model, the free electrons are moving inside the metal surface with a high speed. Okay, with high speed, and these free electrons move inside the metal surface, and the metal surface is actually inside the metal surface there is actually a uniform background of positively charged ions. Okay, so in course of motion, these free electrons actually collide with the lattice, or you can say the positively charged ions, and this collision is very frequent. It means since there is a large number of ions and large number of electrons too, so the collision between the ions and the lattice, or ions and the collisions between electrons and the lattice, or you can say electrons and the positively charged ions, is very frequent. In fact, almost 10 to the power 21 collision takes place almost in 1 second. So this is the frequency of collision is very high. As you can see in this figure, I have shown just a symbolic figure here, that all these small spheres represent the ions. These are ions, or you can say these are the lattice points. Okay, and let us say that an electron starts from here and collide another ion or this lattice at this point, and after collision the direction of the motion of the electron is randomly changed. Okay, and again here it collides with another ion. Okay, and then again the direction changes, and then it collides another ion at here. So in this way an electron suffers so many collision with the ions. Since between the two successive collisions, let us say this is the path between the first and the second collision, since since no force acts on the electron between two successive collision, so the path connecting the two sides of collision, two successive sides of collision, is called free path. So this first one is free path, this is second free path, this is third free path. Free means free from collision. And when there is no electric field applied to the conductor, and in electrostatic condition, inside any conductor electric field is equal to 0. So this electron does not experience any force, and that's why the path connecting the 2 points of collision is called a free path because the electron does not experience any force, and that path in absence of force is a straight line. Okay. So in general you can say that the electron suffers so many collision, and as a whole the path followed by the electron is a zigzag path. Okay. Although the path between two successive collision is straight, but when you will consider, let us say this is point A, this is point B, this is C, this is D. So when you will consider the path of the electron followed by it between points A and D, that will be a zigzag path. Okay. But the path between A and B is a straight line. Okay. Between two successive collision is a straight line. So the electron actually has random motion, okay, in absence of the electric field, and in this condition there is an equal probability of motion of electron in any direction. So if you consider, let us say this is a section inside the metallic specimen, okay, then the probability of moving of electron from left to right, this is L to R, and the probability of motion of electron from this R to L is same. In other words, you can say that in absence of any external field, electric field, the number of electrons passing through a section or crossing through a section from left to right and from right to left is same. And as the equal number of electrons passes from left to right and also from right to left through the same section, so you can say that the net flow of charge, total flow of charge through a section, particular section, is equal to 0. In other words, you can say that the total no charge flows through a section in a particular direction. But you know, electric current is constituted only when there is a net transfer of charge in a particular direction through the section of the conductor. So in this condition, when no electric field is applied across the conductor, then due to the collision, the motion of the colliding electrons or the conduction electron is random, and there is no net charge flow or net charge transfer in a particular direction. And that's why I have written here that the net charge flowing through this section in a particular direction is 0, and as Q is 0, then you know, according to the definition of electric current, I is equal to dq by dt, but since Q is 0, so I will be 0. So you can say, although electrons are moving very rapidly, very fast inside a metallic specimen in absence of any external potential or external voltage or external field, but no current is constituted. When you consider, let us consider that this is a metallic wire, and you have not connected this wire to any external battery. If I will ask a question, are electrons moving inside this metallic wire or not? Answer will be yes. Electrons are moving inside this wire. Then I will ask you, the electrons moving inside this wire is constituting electric current? Answer will be no. If we will consider, we will take a metallic wire, no current will constituted, no current will flow through the wire. But now let us consider that this metallic specimen is connected to an external battery. See here, this let us say this AB is a metallic specimen, and I have considered here a cylindrical metallic specimen for simplicity. And I have connected the two ends, that is A and B, to a battery, or you can say a DC source. Okay, this longer line represents the positive terminal of the battery, and this smaller line represents the negative side. Okay, so you can say that this end A is at higher potential and this end B is at lower potential. Okay, this plus sign actually represents the higher potential state and minus represents the lower potential state. And whenever there will be a potential difference, then electric field will be produced. So inside this conductor now an electric field E will be produced, and that electric field will be directed from higher potential end A to the lower potential end B, because electric field is always in the direction of decreasing potential. Okay, so you can see, although in electrostatic condition, when you do not connect the specimen by a battery, then electric field inside the conductor is zero. But when you will connect the specimen by this battery, then the electric field inside this conductor is not zero. It will be non-zero, and it will be directed from higher potential to lower potential. So according to this figure, an electric field will be produced, and that electric field will be directed from end A to end B. Okay, I have shown this in this figure. I have assumed that the length of this specimen is L, and we also considered that the area of cross section of this metallic specimen is S. We also consider for calculation. Okay, now you can think that an electric field is present inside this metallic specimen, and inside this metallic specimen, according to Drude model, electrons are moving randomly, but electrons are the positively charged particle. This is one of the basic difference between the gas molecule and the electron. Gas molecules are not charged, but electrons are negatively charged. So now you can say that these free electrons found themselves inside an electric field, and so they will experience electric force. What will be the electric force experienced by the electron? F will be equal to minus E small e times capital E, where minus E is the charge of electron and this capital E vector is the electric field vector. Okay, so each electron now experience this electric force. So now motion of the electrons are not free, but that motion is now under the electric force provided by the electric field. Okay, and what will be the magnitude of this electric field? This will be simply equal to voltage divided by length, or potential difference divided by length. You have definitely studied these things in your lower classes. Okay, so now the electron experience this force, and due to this force, now the motion of the electron gets modified. You can say the random motion will get modified, since this force is in against of the electric field, because due to this minus sign, you can say that this F is anti-parallel to electric field. So now the electrons are will drift in against of the electric field, that is from B to A. But regarding this, there is also a misconception here. I have actually shown here that if V is the voltage applied across the specimen, then the electric field developed is equal to V over L. I have multiplied by the unit vector I here because we have considered that this metallic specimen is lying in X direction. Okay, and so the force experienced by each free electron will be equal to minus E times capital E, and this will be minus EV by Li. Okay, and therefore this F is anti-parallel to E. Okay. So now, as I have told you, that now the electrons are experiencing this force, and due to this force, the most random motion of the electrons get modified, and there will be now a net transfer of electron in a particular direction. If you consider that there is a section, let us say like this, in this Mn inside this conductor, then there will be a net flow of electron from B to A, and as there will be net flow of electron from B to A, because the electron experiences force from B to A in against of electric field, so now there will be a net transfer of charge from B to A in the opposite direction of the electric field. And if there is a net transfer of electric charge, you know electric current will be constituted. Okay, and so our conductor now conducts the electricity. So in this way, this Drude model explains how the conductor conducts the electricity in presence of this external electric field. Now here, in presence of this force, the motion of the electron is not random. Okay, now it is under electric field, and some books and authors claims that the presence of electric field, in the presence of electric field, the path of free electrons is becomes a straight line in opposite direction of the electric field. But this is not true. You know, the path followed by a particle moving under a force will be a straight line only when the force applied is either parallel to the velocity of the electron or anti-parallel to the velocity of the particle. Only then path of motion will be a straight line. It means when you apply a force in the direction of velocity, or you apply a force just in opposite direction of velocity, then path is a straight line. But if you consider that a particle is moving with velocity v in this direction and the force acting on it is in this direction, can you say that the path followed by this particle is a straight line? Answer will be no. Okay, you have definitely studied the projectile motion, where the angle between the force of gravity and the velocity continuously changes, and so the path followed is a parabolic path. So actually what will be the path? That depends between the angle between the force and the velocity. Okay, so in general here you can also say that the path followed by the electron will be now in general a curved path or a parabolic path, although all those electrons which have velocity on the line of electric field, they will actually follow strictly the straight path. But in general, the path followed by the electron between two successive collisions, even under the electric field, will be not straight. That will be actually parabolic in general. So I have shown in this figure, you can see that if electric field is 0, then this dotted line represents the path of the electron between two successive collisions. So here there is an electron and collision takes place at these points. Actually this is these are the points of collision. Okay, and between these 2 points, this dotted line path will be followed by the electron if there will be no electric field. Okay, but this full line curve represents the path of the electrons between two successive collisions in presence of electric field. So you can see in this figure, in presence of electric field, the path followed by the electron between two successive collisions in general is parabolic, or you can say curved. But if there is no electric field, then you know these paths will be straight. Okay, so don't be confused that when electric field is switched on, abruptly the path of the electron will become straight. That is a wrong concept. It is not always. It is possible that for those electrons which have velocity lying on the line of applied field, that will follow strictly the straight path. Okay, but all those electrons which have velocity on and in another direction of the applied electric field, those will follow in general the parabolic path. Okay, but now the motion of the electron is governed by the applied electric field, and so definitely they will not now move with the thermal velocity Vrms, but their velocity will get modified. And under this electric field, when electron move, you can think the electron is not moving in a free space, but these electrons are moving under the electric field in a medium where where there is a uniform distribution of positively charged ions. So in course of motion, these electrons collide with the ions. So actually here two phenomena take place simultaneously. Due to the electric field E, the electrons get accelerated. Okay. On the other hand, during this acceleration, the electron gets collided with the ions, and due to that collision, the motion of the electron get retarded. So this acceleration and retardation, why acceleration? Acceleration due to the electric field. And why retardation? Retardation due to the collision of electron with the ions. So acceleration and collision take place simultaneously, and due to collision there is a retardation. So in fact, the two processes, collision and acceleration, result in a dynamic equilibrium in which a uniform average drift velocity is achieved by the electrons. Are you getting our things or not? Our electric field accelerates the electron, but collision retards the electron. So finally, due to these two processes, electrons move with a constant velocity, V equal to constant, and that constant velocity is called drift velocity. So actually drift velocity is defined as the average constant velocity or uniform velocity acquired by the electrons inside a metal by the application of electric field which is responsible current through it. In this way you can define the drift velocity. What is this drift velocity? Can you say? Drift velocity is an average constant velocity under the electric field. In brief, you can say drift velocity is the constant velocity of electron under the electric field. When the electric field will be switched off, the electron will be again in random motion, and that velocity with which the electron moves during the random motion is not drift velocity. But when you switched on the electric field, the electrons move under this electric field, and the velocity of electron moving under the electric field is simply called drift velocity, and it is a very small velocity. You will see later on that its magnitude is of the order of 10 to the power minus 4 meter per second. Actually, for calculating the electrical conductivity and verifying the Ohm's law, it is necessary to know about this drift velocity. So I am talking here about the drift velocity. So first of all, we will find the expression for this drift velocity in two ways. First of all, we will find the expression for drift velocity in terms of the current density, and after that we will obtain the expression for this drift velocity in terms of an atomic constant, which is also called relaxation time. Okay, and then comparing those two results, you can easily see that this Drude model actually explains the Ohm's law and the electrical conductivity of metals. Okay, so now let us consider that this Vd is the magnitude of the average drift velocity of electrons in a metal. Okay, and S is the area of cross section of that metallic specimen, and we assume that this small n is the number of free electrons per unit volume. You can also say it that this is free electron density, and E is the magnitude of charge of each electron, or you can say this is electronic charge. Okay, now you know from definition of electric current, I is equal to dq by dt. But what will be this dq by dt? You can see, if you consider that this is your specimen, okay, and it has area of cross section S, okay, and the electrons are moving in this direction, you can consider, and we have to find how many electrons passes through this cross section, let us say AB, per second. Number of electrons crossing through this section per second we have to find. How we can find? Let us consider that the length of this cylinder is equal to let us say Vd. How much? This is equal to Vd. What does it mean? It means, since it is drift velocity, so an electron which is lying here at 0 time, that will be here at 1 second. So the distance covered by it in 1 second will be equal to this Vd. Okay. Now volume of this cylinder will be what? If we assume that volume is V, that will be S into Vd, and this is actually the volume described by the electron in 1 second. Okay, so the number of electrons lying in this cylinder will be what? That will be N into S into Vd. N into S into Vd. Okay, and what will be the charge of these electrons? Since this is number of electrons, so when you will multiply it by E, then this E into N into S into Vd, this will be the amount of charge that will flow through this section AB in 1 second, and that will be equal to electric current. So I is equal to NE Vd times S. I think we have understand how this result I have been written. Now you know the current density is the current passing through unit area normally. So current density J will be equal to I over S. And you can see, since I is equal to this much, so I over S will be simply equal to NE Vd. So Vd, which is the magnitude of drift velocity, that will be J over NE. Okay. And if you want to write this expression in vector form, you can write vector Vd equal to minus J over NE. Here minus sign actually has been taken since the charge of electron is negative. So whenever you will write the equation in vector form, you must take into account the sign of charge, because if you will not consider this minus sign, the direction of drift velocity will be just reverse. Actually this equation shows that the drift velocity of electron Vd will be anti-parallel to J, and J, you know, this J is parallel to electric current, so you can say that Vd is just in opposite direction of the electric current. So if there is a specimen, current flows through it in this direction, then drift velocity will be in this direction, just opposite. Okay. So drift velocity is in the opposite direction of electric field, opposite direction of electric current, and in opposite direction of current density factor. Okay. But now we are going to find the expression for this drift velocity in terms of an atomic constant, which is also called relaxation time. What is this relaxation time? You can see that if we consider that here the electron suffer first collision, here it suffers second collision, now here it suffer third collision, and here it suffer fourth collision, here it suffer fifth collision. Okay. But the time taken by the electron between two successive collisions are not in general equal. Can you think that always after equal time the electron will collide with the lattice? Answer is no. In general, if you consider that the time taken by electron between first and second collision is T1, and between second and third collision is T2, between third and fourth collision is T3, then in general T1, T2, T3 will be not same. So in calculation we consider or we can take the average value of this time taken by the electron between two successive collisions. Okay. So when you will find the average value of the time taken by electron between two successive collisions, that time average value is denoted by the symbol tau, and that is called relaxation time. Why the word relaxation? Because between two successive collisions the electron is in relaxed state, because between two successive collisions there is no collision is suffered by the electron, so electron is relaxed, and so that this time is called relaxation time. So actually what is this relaxation time? This is the average time taken by an electron between two successive collisions. And the average distance between two successive collisions is denoted by the symbol lambda, and this is called mean free path. You can see my video on mean free path in kinetic theory of gases in the playlist thermodynamics of my channel. You can see. And the electron moves from one site of collision to another with the speed vrms. So if lambda is the mean free path, then this relaxation time tau is equal to lambda divided by vrms. Okay. This tau, which is called relaxation time, the value of relaxation time is different for different metals. Actually, the value of tau depends on the nature of metal, and so that it is called an atomic constant. But for a particular metal, it has a particular value at a particular temperature. It is also temperature dependent. But at a given temperature, for a given metal, tau has a particular value. Tau is constant, and that's why it is called atomic constant. Now our aim is to find the drift velocity of electron in terms of this tau. Okay. So let us see how now we can find the drift velocity in terms of tau. Okay. For this we will write the equation of motion of the electron moving under the electric field E. As I have told you earlier in the postulate of Drude model, that Drude has assumed that electrons are classical particles obeying the Newton's laws of motion. So here, when your aim is to write down its equation, dynamical equation of motion, you must think about Newton's laws of motion. So the force acting on the electron will be given by this second law of motion, F equal to ma, where a is the acceleration of the electron and m is its mass. But You know, under the electric field E, force acting on the electron is minus E times E. So minus E times E is equal to ma, and that's why you can say A is equal to minus E times E over m. But from the definition of acceleration, you can say that this A is equal to dv by dt, because acceleration is the time derivative of velocity. And so dv by dt is equal to minus E divided by m. Okay. Now, if you think that this V RMS is the thermal velocity of the electron and T is the time between two successive collisions, then you can integrate this result between time 0 and time t. Actually, at t equal to 0, that is initially when the electric field is just switched on. In fact, in that condition, electron was in thermal motion and its velocity was v RMS. But as at t equal to 0, electric field has been applied, then at any moment t, its velocity gets modified, and we consider that at any time t, its velocity is v. So this dv has been integrated under the limits v RMS and v. But v RMS is the velocity of the electron just in absence of the electric field. That is at initial moment when the field is just on. And so the corresponding time is 0. Okay. And at time t, the velocity has become v. Okay. So corresponding to t equal to 0, the limit for velocity is v RMS, and corresponding to time t, the limit for velocity I have assumed v. Okay. Now you can see this integral will be v, and when you will put the limits, what will be your result? This will be v minus v RMS, and that will be equal to minus EET divided by m. And so that v will be equal to v RMS minus EE over m times t. Okay. Now, as you know, according to definition of drift velocity, it is the average velocity of the electron with which it moves inside the metal surface under the electric field. So if now your aim is to find the average drift velocity, you must take the average of equation 4 for the total number of electrons. Okay. So averaging V over large number of electrons, what will be our result? This is average value of V, this is average value of V RMS, and then you have to take average value of this T. Okay. But when you will average V over the large number of electrons, your result will be actually drift velocity Vd. So this Vd is the average drift velocity, average value of V. But you know, V RMS is the velocity due to random motion. Okay. And that motion is taking place almost in all directions. So the average value of V RMS for a large number of electrons will be simply equal to 0. So average value of V RMS is 0, and you know the average time taken between two successive collisions is called relaxation time. So the average value of T is equal to tau. This is relaxation time. Okay. And so the average drift velocity from here you can see will be equal to Vd, and that is equal to minus E tau over m into E. Okay. And so you can see that this Vd is proportional to E. So whenever E will be 0, Vd will be abruptly 0. So you can talk about the drift velocity only when the electric field is present. If you will not apply the electric field or the voltage, you cannot talk about the drift velocity. So drift velocity is meaningful only when we have connected our conductor by an external source, external battery, or you have produced the electric field inside the conductor. In absence of that electric field, you can't think about drift velocity. Okay, so this is the expression for drift velocity in terms of tau, which is called what? It is called atomic constant. Okay. Now we have two expressions for drift velocity. One expression we have obtained in this equation A1, and one expression you have obtained earlier in this equation 2. So now you can equate these two equations because both of them define the drift velocity. So equating equation 2 and equation A1. In equation 2 you have seen that drift velocity is equal to this much. This is J over NE, and according to equation A1 it is this is minus J over NE, and according to equation A1 it is minus EE tau by M. Minus minus will cancel out in both sides. So J over NE is equal to EE tau divided by M, and so J will be equal to NE square tau over M times E. You can see. Now this NE square tau over M is replaced by sigma, and so J is equal to sigma times E. Actually this sigma is nothing. This is called electrical conductivity of metals. This is called electrical conductivity. And this equation J equal to sigma E, what is this? This is actually the vector form of Ohm's law, or you can also say microscopic form. This is called microscopic form of Ohm's law. Microscopic form. Okay. So in this way you can see this Drude model explains the vector model or the vector form or the microscopic form of Ohm's law. Okay. Now you can also see that this model explains the electrical conductivity. This is the expression for electrical conductivity. On what factors, on what quantities electrical conductivity of metal depend, it is clear from this equation A3. Now we will also see that this Drude model from the Drude model we can derive the scalar form or the macroscopic form of Ohm's law. See it here. As this equation A2 can be written like this: J equal to 1 over rho into E. Here rho, which is actually reciprocal of sigma, it is called electrical resistivity. It is called electrical resistivity. And in a scalar form, you can write it as J equal to E over A, rho. But you know, J, which is magnitude of current density, that is equal to I over S, and E is equal to V over L. You have seen. So I over S is equal to V over rho times L, and therefore you can say that V is equal to this much. This is rho L over S into I. This rho L over S is denoted by the symbol R, and this is actually called the resistance of the specimen. So V is equal to Ri, and you know this is the well-known Ohm's law in in a scalar form, or you can say macroscopic form. Macroscopic form. So you have definitely been very pleased now how we can explain the electrical conductivity sigma and Ohm's law on the basis of Drude model. Okay. So in this lecture we have seen two things. First of all, you have seen what are the basic postulates of Drude-Lorentz theory, and then you have explained the electrical conductivity and Ohm's law by using this theory. But in the second part of this lecture, we will see the other applications of this Drude model. Okay. So thank you very much.